Graphing techniques and transformations. Okay, so first let's look at how to write the equation of a function given the transformations that are involved. We're going to use the basic parent function y equals x cubed and write the equation for the function, for example, that is shifted right 4 units. Before we do that, let's remember that the basic transformation equation looks like this. Y equals a times the quantity b times the quantity x minus h, that's all cubed, plus k. So that is the transformations involved in the cubic function. So shifting right 4 units, that means my h is 4, and that equation would look like this. Y equals x minus 4 quantity cubed. That's it. That is the cubic function shifted right 4 units. So the h shifts, does a horizontal shift left or right? Okay, next, shifted left 4 units. So instead of going right, we're going left. Here we would have y equals the quantity x plus 4 quantity cubed. So again, that h tells us whether we are shifting left or right. Okay, now let's look at this function shifted up 4 units. So k tells us how we're shifted up or down. And here, because we're going up 4 units, k will be 4. So y equals x cubed plus 4. Down 4 units, again, we're looking at k. So y equals x cubed minus 4 for down 4 units. Reflecting about or over the y-axis. Okay, this will be a negative in the b spot. So y equals the quantity negative x cubed. We could simplify that to y equals negative x cubed, but I think the first way of writing this shows that you understand that we are reflecting something over the y-axis. Next, reflecting over the x-axis. That is putting a negative in the a position. So y equals negative x cubed. Vertically stretched by a factor of 4. So a will be greater than 1 if we are vertically stretching the function. A will be less than 1 if we are vertically shrinking a function. Because we're stretching by a factor of 4, a is 4, so y equals 4x cubed. Okay, horizontally stretched by a factor of 4. So we are now going to deal with the number in the b position. B will be greater than 1 if we are horizontally compressed, and b will be less than 1 if we are horizontally stretched. So here, because we're stretching by a factor of 4, b will be 1/4. Y equals the quantity 1/4 x quantity cubed. Okay, dealing with the same parent function, let's look at combining some of these transformations. So first, y equals, let's show that we are shifting right 4 units. So I will have x minus 4, reflect about the x-axis. So I will have x minus 4 in parentheses cubed. I'll put the negative out in front in the a position, and then shifting up 2 units, that's plus 2. Okay, first we're going to look at shifting left 1 unit. So y equals x plus 1. Reflect about the y-axis. So I will put a negative in the b position. So we have all of that cubed. Vertically stretched by a factor of 3. So I have a 3 in my a position, and shifting down 4 units, I will have minus 4 in the k position. So y equals 3, parenthesis negative, parenthesis x plus 1, quantity all cubed, minus 4. Okay, now we will reflect about the x-axis first. So y equals the quantity negative x cubed, We will so reflect about the y-axis as well. So I'll put the negative in the A position as well. And then shifting up 5 units plus 5. Okay, for the last one, horizontally stretched by a factor of 3. So 1/3 goes in the B position. So 1/3 x quantity cubed. Reflect over the x-axis, put a negative in the A position, and then shift up 4 units plus 4. Okay, finally, let's look at how we would use transformations to graph a function. And we would be doing this by hand if we were face to face. So we are going to graph f of x equals 3 times the absolute value of x plus 1 minus 3. So we have 3 in the A position. That means that this function will be vertically stretched by a factor of 3. We have plus 1 in the H position, so this is shifted left 1 unit. And there is a negative 3 in the K position. This means that this function is shifted down 3 units. We will first start by graphing the parent function, which is f of x equals the absolute value of x. This is one of those parent functions that you should now be familiar with. So we have a point at the origin, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4, negative 5, 5. So this is my V-shaped absolute value function. Then to do the transformations, we need to go in the order of operations. So next, we would shift left 1 unit. So I'm going to take all those points that I graphed or plotted for the parent function and literally move each of them left 1 unit. So you will visually see me moving every single point, putting it in red 1 unit to the left. So here is our transform shifted to the left 1 unit function. But next, we will now vertically stretch the function by a factor of 3. When we're vertically stretching, we're looking at the distance a point is from the x-axis, and we are going to triple that distance here. So the first point, which is at negative 1, 0, I'm looking at the vertex first, it's not off of the x-axis, so it's going to stay there. So I still have that point. But then my negative 2, 1, I'm going to triple that distance to make it negative 2, 3. And then my point that's at negative 3, 2, I'm going to triple the distance and make it negative 3, 6. And I will continue tripling the distance that the red points are from the x-axis. And that leads me to this blue function. So this blue function is the absolute value function shifted left 1 and vertically stretched by a factor of 3. We have one more transformation left. We are now going to shift all of the points on the blue function down 3 units. So I'm going to take those distinct points and shift everything down 3. Starting with the vertex, shifting all of them down 3. When we're doing it by hand, I usually ask to see at least 3 distinct points. 5 is often better. I have more. But that green function is our final transform function, which is the absolute value function shifted left 1 unit, vertically stretched by a factor of 3, shifted down 3 units.